So our first speaker today is Rick Alter. So he has had a wide range of career working from ASICs and all the way to UX. And he worked at Google for 9 years on the machine management and health monitoring, where he also led the unification of OpenBMC as a Linux Foundation project. Now he works at Clipsium as a security researcher, working on FPGA bit streams. And he's going to talk today about how to avoid common vulnerabilities in BMC systems.
Thank you, Benjamin. So as you said, I'm Rick Alter with Clipsium. Clipsium's just we won't talk about them too much. We'd like to keep our research separate from our marketing. So being the BMC track, I assume most people are at least somewhat familiar with BMCs. Still going to do a slight recap. But the main thing is that BMCs are a way of providing your remote management functionality for a server, right? And a lot of the drive for these systems was actually to control various aspects of the system that were things like fan control, temperature, or environmental management, and sort of automated processes. But once you have a system available that takes care of that and runs outside the host processor, then you can start adding nice to have features for IT functionality. So your remote hands capabilities like virtual consoles, virtual media, updating host firmware. So a BMC ends up being a fairly comprehensive device. So just a touch on terminology. When I say host, I mean the computer that you're actually intending to boot and run an OS on. But a server contains both a host and a BMC. And in some cases, you might have a chassis that actually has its own independent BMC and may contain more than one server. So if you had blade servers, for example, there'll often be a separate BMC associated with the chassis itself. Because I'm likely to reference them throughout my talk, these are just some of the common SoCs in use, some more recent than others. But there's only a handful of vendors that actually produce silicon for BMCs. Most people are familiar with ASPEED, as that's pretty widely used. HP actually makes their own silicon, and then Nuvoton also has products that are out there. Most of these are ARM-based. They do also have coprocessors in some of them. So you end up with sort of a mishmash of CPU architectures that you can play with in these devices. Okay, why would I attack a BMC? So I'm coming at this from a security perspective. So a BMC, if it offers remote management capabilities, it must be highly privileged as far as access to the host. And if I look at the feature set that's available, yes, I can not only interact with it from a keyboard, video, mouse perspective, but also things like accessing the host firmware and other systems on it. Usually a BMC is network accessible, right? It's supposed to be out of band, and the whole point of the remote management is that I don't have to be there, so it's usually connected to a network that is reachable. Now, assuming that I compromise a BMC, it's really a computer that's separate from the host computer. So if I compromise a BMC, I get persistence independent of the host. You can format the disks on the host, you can replace the firmware. It doesn't matter if I'm on the BMC, you have to actually replace the BMC's firmware to actually eliminate that persistence as well. And BMCs tend to have a poor firmware security history. We'll get into this a bit later, but one of the key points is even when security vulnerabilities are found and firmware updates are produced, they're usually deployed very slowly, if at all. And they're often overlooked as, is there even an update available? So there's lots of research in this space around BMCs. So back in 2013, there was a report on IPMI and a lot of the classic vulnerabilities there. Rapid7 actually has a penetration tester's guide to tell you, here's how to run the tools to actually perform a variety of common attacks against systems when you're doing a red team penetration test. And more recently, there was a group from Airbus that went through and figured out ILO4's firmware, reverse engineering the operating system on it, and found numerous vulnerabilities that were able to compromise the ILO4 systems. So my intent is to raise some awareness of the classic vulnerabilities that we run into. And the thing is that these vulnerabilities keep repeating over time. Well, the very first class of these is simply that if you implement IPMI to the spec, you're gonna run into security problems. Is anybody not familiar with that? Anybody familiar with the IPMI security vulnerabilities? Oh, a few hands. All right, all right. Okay, so first of all, RMCP plus or an RMCP both have, those are the protocols used to talk to IPMI over a LAN interface, so over a network. And the actual specification requires a few crypto protocols and hash functions, and others are optional. But given that the standard was last updated in 2013, pretty much all of the available options for you, even if you implement the optional ones, are just classic algorithms that either are already vulnerable or very likely to be vulnerable. And in fact, if you implement only the mandatory ones, you are guaranteed that you're using a weak algorithm for at least some aspect of your security. At this point, the IPMI promoters recommend you not actually rely on this specification anymore, right? They're not planning any new updates. You should go implement something else. One thing to note there is both in most of these encryption schemes, you actually see that mandatory type 0 is none, which ends up being a nice hole, as that was interpreted to mean that I don't actually have to authenticate at all on many BMC implementations. So this was found in that you can simply connect with authentication type 0 and it won't ask you for any credentials. Looking past that and we look towards password storage, the required algorithms as part of the IPMI spec include plain text passwords and multiple hashing functions, which means that the IPMI stack has to be able to compute these hashes and has to have a copy of the plain text password in order to be able to actually validate your password. So somewhere on the system, I have a plain text password. Now that tells me that there's interesting things to go find inside of a BMC. This gives me even more of a reason to actually attack them. If that isn't enough, then the RAKP algorithm that runs on top of RMCP plus, when you're actually authenticating to a BMC over the network, has a quirky implementation of HMAC as part of the specification. It actually sends you a salted hash of the user password before you authenticate. It essentially sends you their hash password and then asks you to perform a computation that validates that it's correct. So it turns out that this has been known. This was reported, many, many years ago. And in fact, Metasploit framework, which is a collection of attacks in sort of an automated form, has a script that you can simply run over an IP range, and it will actually collect all of these password hashes for you and dump them out into formats that you can feed into password crackers like John the Ripper and Hashcat. So I went ahead and did this just to see what would happen against my array of test machines at Eclipsium, and found that I could crack all of the 1 to 8 character alphanumeric passwords for about $20. Now, how did I get to $20? Well, there's actually services nowadays for machine learning that allow you to rent machines with large numbers of GPUs attached. And I found one that offered me 91 cents an hour on a four top of the line NVIDIA GPU setup, which meant that I could run this and it was computing about 10 terahashes per second. And so I was able to actually crack all of these in, I think it was, just under 20 hours. So if you're using 8 character passwords, you might want to be thinking about, at least extending that. to hurt the search space. But keep in mind that most systems today still ship with fixed default credentials, right? The default passwords are well known. In fact, Metasploit even checks for those hashes. It just knows what they are. But even when you look at HP's ILO, which actually ships with randomized credentials on a per server basis, those are only 8-character passwords, and they all use uppercase, which meant that I could crack them in about 16 minutes. So this password story in IPMI is just not good. Now, some assumptions about IPMI are that it's there in, well, I guess the IPMI spec says that local interfaces are sessionless. And in the context of IPMI, that means unauthenticated. You just simply can execute commands, and you have no real privilege check. And there is a list of what commands are valid over local interfaces, but by specification, it has no authentication mechanism over the local interface. Now, what that meant is that the host system can just send off whatever commands it wants. Now, in IPMI 2.0, there was an understanding that, oh, well, we also defined local interfaces to include things like I2C out to peripheral cards, which means that a peripheral device could actually send unauthenticated commands to the BMC and can do all sorts of things that you probably shouldn't be able to do. And especially when you start looking at other protocols and transports for these commands, you just run into a bad scenario. So there was this introduction of the firmware firewall, and it's essentially a set of IPMI commands that let you flip a few bits to disable certain commands over certain transports or certain channels. This firmware firewall is actually an optional part of the specification. So you hope that your vendor has implemented this. If they did implement it, the specification makes no recommendations as to what the defaults are. So you're left up to whatever the vendor decided is the reasonable subset of commands that a host should by default be able to run, or that an add-in card should be able to run. In practice, most vendors, if they implement it at all, just leave it wide open. So from the perspective of the host or an add-in card, I have full access to a BMC via IPMI, just from the get-go. This might make sense in a classic IT environment where I have careful IT staff managing the host machine in coordination with BMCs. This does not make sense in a bare metal virtual machine environment. Okay, so IPMI is bad. Just gonna say it. Please stop using it. But let's talk about some other areas. So moving on, how many people have used a BMC's web interface? Hopefully everybody in the room. Okay, great. So we have a web interface on these things. Well, if you pay attention to the web security space, there are a lot of attacks towards web, targeting HTTP and web servers and web frameworks. There's a whole host of new attack types that come in with that space. How have BMCs done in this space? Well, in a typical BMC, you usually have an HTTP server running, and because it's a constrained environment, most of what I've seen is an HTTP server that really only serves static pages and actually implements all of the dynamic functionality by simply executing CGIs. Now, for those who haven't done CGI programming since the 90s, essentially this is the web server is just going to execute either a script or a binary and pass it some variables that indicate the contents of the HTTP variables and other information. And the script runs, and whatever it returns is sent back to the client. Well, in the case of these BMCs, most of the time these CGIs are actually C binaries that have been compiled in. And so it's actually literally just running a binary. So the HTTP server ships out some static content to the browser to build up the DOM. It uses JavaScript to do AJAX type queries to the CGI scripts, which are the C applications that are running. And on some of the more modern ones that have HTML5, KVM functionality, you'll actually see that they also run a WebSocket server and connect over WebSocket to actually do streaming for the actual IKVM instead of connecting separately via VNC and things like that. Okay. Well, if I go look at the OWASP top 10 from the very first list. So everybody familiar with OWASP? Yes, yes. Anybody not familiar with OWASP? Okay, we do have a few. It's in my notes, but they're not showing on here for some reason. That's fun. The Open Web Application Security Project. I don't remember if it's what the P is. But essentially, it's a group that are focused on web security overall as a body, and they publish a top 10 pretty much every year. 2004 was the very first year they published these. This was sort of at the height of understanding that security on the web was going to be different, and it was going to be, and there were a lot of common patterns that were continuing to crop up. And I'm not going to go through all of these, but what's interesting to me is that when I go look at the CVEs for BMCs, we actually match up really well. And I only really grabbed one example from each case. But notice that, for example, buffer overflows is something that's been reported in 2019, right? Cross-site scripting is recent as 2015, many in 2018. Even though we have known about these vulnerabilities for 15 years, right? These classes of vulnerabilities, we keep making the same mistakes. Now, to be fair, if I look at OWASP top 10 for this year, there are still a lot of these classes of attacks on that list. But some of them that we see here are actually things that are not so prevalent on the open web anymore. Now, if I look at one of these in particular, just to show you how simple this is, so on ILO 4, there was an authentication bypass and remote code execution. Now, it turned out that what happened was remember you're actually calling a HTTP server, which is going to run a CGI. And that CGI is a compiled binary. And in this case, it was parsing the request headers using strcomp, stir, and scanf. These are well-known insecure functions that have problematic error behaviors. Well, they were copying the value of the connection header into a 16-byte buffer. But because of the way they implemented it, it wasn't checking the length of what was being passed. So it wasn't just copying the first 16 characters of the connection header. It was copying everything, which meant you could scribble over whatever was after that. So the entire exploit is right there. If you run that curl command, you will actually crash an ILO 4. And if you're very careful about it and pad it just right, you can actually overwrite the security information inside of the context that happens to be stored right next to this connection header field in memory and completely gain remote access into it as well as remote code execution. This is how simple some of these attacks actually are. Now, you might say, well, why is that bad? Well, most of the BMCs I look at run everything as root. The HTTP server is running as root. The CGIs are running as root. There is no reason for this. The IoT world is better at building out privilege separation than this. Right? This is a real major problem. And there's certainly design issues at play here. Like some of the systems use various IPC mechanisms that would be harder if you did privilege separation. But this is really a thing. There is no defense in depth. If I can get one foothold into any process running, any CGI script, I have full access to the BMC. It's that simple. Okay, let's talk about unsigned firmware and updates. So I'm going to pick on Supermicro. I'm sorry, they're an easy target. They are great people. I like working with them. So if I look at a Supermicro X10 BMC, first of all, note that they actually use the same BMC across their entire product line. So it's the exact same firmware image across all of their X10 platforms. Well, if I take a look at the actual BMC update file, it's actually just a dump of a flash image. So essentially, it's going to take this image and just write it out to the flash. Now, it turns out that they have broken it up into sections, as you might expect for a typical embedded Linux system. And that's because it is a typical embedded Linux system. Now, there is one thing that at the end, there's this section called the image tags that basically is self-describing of the image. So by searching for this region in the binary, the updater knows, okay, this section, here's the start offset, here's the end offset, here's a CRC32, and here's what my name of that binary is. It basically tells me everything I need. Can anybody tell me what's missing? A signature, right? Like there's a CRC32, which is going to tell me whether or not a bit got flipped, but there's absolutely no security in this at all, right? So what happened when we looked at X11? Maybe they got better in their next generation. Well, they kind of did, right? So the layout is actually the same as an X10. It's just that they used AES to actually encrypt the very first 96 bytes of each of the file systems, or of the read-only file systems, so they wouldn't be detected as a normal CRIME-FS file system. But the rest of the file system was completely unencrypted. It was only the first 96 bytes. But then, and they also encrypted the image tags. But of course, because I can read most of the file system, and I know that it has to be unencrypted when it actually writes it to the file system, or writes it to the actual flash part, we could just go looking. And what do you know? The actual AES keys and everything are actually in a firmware updater binary that happens to not be encrypted by the encryption. Right? So from there, you can just go ahead and pull all the information out, decrypt it, and again, you're back to, well, yeah, they did encrypt it, but not enough to actually prevent an attacker. Right? It's going to stop someone from casually updating it, but it's not comprehensive in any way. Okay, well, maybe it doesn't matter if I write a bad image, right? Maybe it'll be caught on the next boot. Well, really only the latest BMCs even have secure boot in the hardware. So I listed the couple that I'm aware of. There may be others, but most of the systems that I encounter use ASPEED AST 2500s. It does not have secure boot. It's just simply not an option. The CPU is just going to load whatever the first stage bootloader is and go from there. Now, the other thing is that even if the hardware has that initial stage of the ROM verifying the first stage bootloader, you actually have to fill out a full chain of that verification. So the SoC has to validate the bootloader has to validate the kernel has to validate the file systems. If you've worked with Chromebooks, you know what this scheme looks like. If you've worked with Android, you know what this scheme looks like. This scheme is not implemented on BMCs. And then there's the question of, well, what do you do when the verification fails, right? If I write a bad image and I know that the signature fails, if I'm in an enterprise server product, do I actually want to stop the machine at this point? Should it effectively brick it, or should I actually go ahead and boot the image, but notify somebody that it's actually running unsigned images or been compromised, so that you can come back and look at it? These are actually policy decisions, and this gets into a hard part of this. Some folks are actually afraid of implementing secure boot and a full verified chain because the recovery story is hard. That shouldn't really stop us. We should be building things to be as secure as possible and figure out what the right mechanism is, right? I'm sorry? You could have redundant images. Like, that's certainly a way to solve this problem, but that requires you to put down bigger flashes. And what do you do if both images are broken, right? So there's ways of solving this problem. It's just that people haven't done it for the most part.
You can have a golden image.
You
can have a golden image for recovery.
You could. There's certainly ways of solving it. I mean, I know that there are. It's just, how many servers do you know of that implement any of those schemes on their BMC? All right. Management networks. When you typically deploy a BMC, the common guidance is do not put the BMC on your main data network. Instead, put it on an isolated management network that then you restrict access to, because we know BMCs are insecure. So just segment it. Okay, all right. So I go through the expense of putting in my extra switch and running all the extra cabling. And this also gives me a nice ability that if for some reason I bring down the data plane and I need to be able to hit management, I can. So usually that management switch would actually have a path to the BMC and the data switch, because switches have BMCs now. Okay, well, but what does this give me from an attacker's standpoint? Well, let's talk about advanced lateral movement. So imagine I have two servers in the same rack. They could actually be in different racks, but assume that I have two servers in the same facility. So one of the servers is mapped directly out onto the internet. It's your front end serving traffic. And the next server over is actually only connected to your internal network, right? They're isolated as far as the data networks are concerned. So no traffic can actually get from the internet directly into your private cloud. There's just no hop there. And if I gain access to these servers, they don't have a direct path, even over their data network, right? But if I can compromise the server that's actually connected over to the internet, I can leverage the BMC network to actually go and attack all the other BMCs that are on that same network. So you've actually given me a backdoor into this. So ultimately, this is kind of a planning exercise problem of, if you're building out a separate management network, you actually have to build out separate management networks that also think through the attack vector of what data network would I be coming into and what would happen if the host was compromised. But we don't usually think about that, right? We're usually thinking about a single management network as a backup option, but it actually provides me as an attacker a nice feature. So how many BMCs? But that doesn't actually matter that much when people just put their BMCs on the internet. There's actually 92,000 of them per Shodan as of about 2 weeks ago. So, I can just go ahead and connect to them. And remember all those wonderful IPMI attacks? There's a lot of them out there. All right, so management networks. But what if I come at it from the other direction, right? We can trust the host. Well, talked about that a little bit when we talked about local interfaces, right? What about in a case where I am running a bare metal virtual machine? Now I'm running code that I don't trust on the host. And in fact, I'm relying on the BMC as a mechanism to regain control of the system. Well, that's certainly one model that we can talk about. If I'm relying on it as my sole control mechanism, then that's somewhat problematic, right? I just don't want to trust the host. Well, but there's also the cases of, well, what if I compromise a host? Right, this gets it back to the advanced lateral movement. If the host is compromised, then being able to compromise the BMC from the host gives you an additional step, and we can close that door. There's not a whole lot of reason that we need the level of access that you would need to go from the host to the BMC. Most of the time, that's not necessary. There's also times where we just, from a deployment strategy, we may not want to actually trust the host, even in a single environment. You might have an IT group that manages the hardware. They use the BMC to keep control of it, but they actually have the OS side of things, the host side, handed off to a separate business unit that maintains that on its own. And it really starts to look like a bare metal VM model, but maybe it doesn't actually have all the fancy features of allocating UVMs and things like that. But you still have the same problem of the BMC should not be implicitly trusting the host. Well, why? What sort of attacks can we do? Well, NCSI. So NCSI is a wonderful feature to let you use a single network interface for both your host system and your BMC. Well, the host by default is going to receive all its traffic, and the BMC sends some careful packets over its NCSI interface to say, please filter this traffic and send it to me. Well, it turns out that some folks are working on the Raptor Computing Talos workstations, really are wanting to figure out or be able to release open source firmware for all of the components in that system. So as part of that, they began reverse engineering the Broadcom gigabit Ethernet chip that's on that system. And so that's called, Project Ortega documents this. They're doing it as a clean room implementation where they've done the reverse engineering with one team, writing up documentation, that another team is then taking to actually implement a clean room version of the firmware. Well, out of curiosity, I started poking through the documentation. And it turns out that inside of these chips, there are actually multiple cores, and it's actually a mix. There's actually 2 MIPS cores and a Cortex M3 inside of one of these things. And all of these can boot from firmware images stored in the actual EEPROM attached with the gigabit controller. but they also have the ability for the host to push firmware to them. Well, that makes sense in the context of this is a NIC for the host, right? So the host should be able to go ahead and update the firmware on it. But the way NCSI is implemented inside of this NIC is actually that the Cortex-M3 gets its firmware normally from a PCI option ROM, and that firmware is unsigned. And it just so happens that that firmware is what actually handles the traffic from NCSI. So all of the NCSI traffic gets processed by firmware that can be changed by the host. Now, if I have a hostile host, it takes some work, but I can intercept all management traffic to and from your BMC. Okay, that's not good. But there's even more. So MCTP. MCTP is kind of a complex topic, but we're going to focus on one part of it. So at its core, it provides sort of if you think of like the concept of an overlay network, you're essentially building a routable network out of various types of buses and connections on the system. So it carries traffic over I2C or PCIe or whatever's available to you. In the case of PCIe, MCTP is handled through vendor-defined messages. And these are specified in the PCIe base specification. So essentially, you have a way of being able to send these messages that are intended as carrying data that's not really defined by the spec, and it's not really part of the main functionality of the device, usually. Some sort of out-of-band data, but you're carrying it over PCI. Well, VDMs, by their nature, can be routed in a couple of different ways. Now, the common use in PCI is that you send data to the root complex, and that's to get access back to the host, right? The host is going to interact with whatever your PCIe devices are. But you also have things like a broadcast from the root complex when you're trying to actually communicate data downward. But more interesting is when you end up in a case where you're using peer-to-peer traffic. So you're actually addressing MCTP or you're addressing VDMs to from one device to another. Well, it's using the peer-to-peer functionality in PCIe. And this is available to allow high bandwidth devices. You can do like offloading where your SSD can actually push the data directly into your NIC without passing through the CPU and the system memory. But there's also security implications of having that open. So in modern systems, when you're running things like virtualization and you're running VMs and you're doing device allocation, you'll often disable peer-to-peer traffic and force it to go back through the host as a way to enforce some security on isolating individual devices. Well, the root complex gets to make that choice, right? And the root complex is actually owned by the host. So the host has an option to say, peer-to-peer traffic isn't allowed. Well, then how does device by ID routing work? Well, instead, these VDMs that are device by ID routed get sent up to the root complex, who's then responsible for turning them around and sending them back down. In concept, this has never been demonstrated yet, but in concept, this means that the host via the PCIe root complex has the ability to intercept MCTP traffic, even if it wasn't supposed to. So just to make this a little bit more clear, so in a case when you have peer-to-peer and the root allows it, the BMC is going to send, say, NCSI traffic over MCTP, and it's going to send that up to the PCIe switch, which is then going to just immediately short-circuit it back down to the NIC, and it's going to handle that VDM and probably send a response back. But in a case where you disable the peer-to-peer traffic, it has to actually punt it all the way up to the root complex, and the root complex has to push it all the way back down. So with all these in mind, and we keep making these mistakes, right? We keep trusting the host, we keep building out management networks, we keep making web security mistakes. How do we evaluate our designs to actually figure out where we need to pay attention, and how do we think about what's going to be an actual attack vector for a system? Well, I'm going to make a few assumptions about a threat model for BMCs. So first of all, if you have to open the case of the server, I'm saying that's out of scope. right? That's physical attack. Now, the reason I say case open is because there are ports accessible, and physical presence where I just plug something in is a lot simpler than actually opening the machine and flashing the BIOS, right? So only the latter case is going to be out of scope. I'm going to explicitly include bare metal VM use case. I am going to assume that the BMC is primarily used for control of the system and that the host is potentially hostile and should be treated as such. I'm also going to assume that the BMC is the highest value device in the server. I don't mean from monetary cost, I mean from attack perspective. It's the most privileged thing in the system. If I can get control of the BMC, I'm very, very, very likely to get control over the host, and I may be able to entirely subvert the root of trust that the host uses to validate itself. So this is a typical SOC architecture. Sorry for the eye chart. It's hard to fit everything in there. But things in black are actually the components that are truly what the BMC firmware itself runs on, right? This is the CPU and the flash part for the BMC firmware and its local memory. Sometimes they even have a USB host port. Things in dark blue are sort of the local peripherals that it's using to control the overall system, like fan control, monitoring voltage sensors and things. In light blue, we have the Ethernet interfaces, could be NCSI, could be a physical jack. And then the things in green are really sort of these peripherals that exist in the BMC, but are in some way used by the host, right? They're intentionally a place where those security models are going to meet. Well, this starts to define a couple of boundaries. And so, part of threat modeling is actually establishing points where you need to look at the transitions from one domain to another. So in this case, we see, the host primarily comes over PCI Express, LPC, USB. With LPC, you could also expand that to be eSPI and all of the other low-speed buses. So that's certainly one boundary that we should be looking at. But over on the other side, we see that there's also the physical connectors on the server, right? So what do I actually have in terms of the physical serial port, right? That's a domain that I cross if somebody can physically plug into it. And then that also includes the USB host port for the BMC. If it's physically populated and accessible, then that becomes an attack vector. And then the network interface itself is really its own attack space, right? It offers remote attack. So if we start digging into these and we look at, well, what can the host do to the BMC? So if I start asking myself the questions, okay, if I look at LPC and eSPI, most of the time what you're routing over that is things like firmware access and classic I/O ports. So what I/O ports are even available to the host? Have I actually restricted that to the minimum subset that I need? And maybe I have to have it more open during an early part of boot and then close it back down, but just completely assume that the host is hostile. Like, what could it do via those I/O ports? And how would that affect the BMC? And then what BMC software acts on that? If I'm exposing a virtual serial port to the host, how that virtual serial port driver becomes an attack vector. I just have to find some exploit in it. Similar things with PCI Express. What address mappings am I pushing out? How many of you have looked at the address mappings that a BMC pushes over its VGA interface to the host? Yeah, there's like 2 hands, 3, 4, 5. Okay, a few. How many of you knew about the pants down, the A-speed hole, right? So part of that is actually accessible through the PCI space, right? Why? Why did it take us so long to actually deal with that problem? Have we sufficiently restricted the capabilities of these address mappings in the BMC address space? So keep in mind, these are address mappings. Maybe I need to have them. Maybe I need to be able to access a memory window inside the BMC. But when the host makes a request, have I restricted it so that, say, the DMA engine inside the BMC can only access the memory window that I've actually granted to the host? Often the case is no, and I can actually arbitrarily perform DMA reads over the entire BMC address space. Again, what software is running over these shared peripherals? What can I do with it? Any device driver, any user space software, any data that comes via these interfaces has to be treated with suspicion and needs to go through strict validation. USB Virtual Hub. I mean, you're acting as a USB device. If I'm a mass storage device, what does it look like when the host sends me traffic? Am I handling that correctly? How much faith do we have in the Linux gadget stack for attacks? What about over the LAN? Well, what services are accessible, right? Just like what ports are even open? Do these need to be open externally? Can I make them local host only? Could I do it via some other mechanism? If I get a request over some network service, how do I actually know that that is an authorized request? Am I making an assumption about session state that I held onto a credential somewhere? Or am I actually looking at, oh, it carries the credential inside of the message and I need to validate each individual request? If I'm an unauthorized user, what information can I learn about it? Imagine somebody plugs this in on the internet and they start running port scans and they start playing with these protocols. What can they actually learn about the system? Today, it's a lot. The more you can restrict what an unauthorized user can actually learn about a system, the harder it is to attack it. When I do export these services, am I actually restricting it to the intended functionality? Did I build the service in a very generic way, but I really only ended up using it in one specific way, like the customer-facing feature is very restricted, but the underlying concept is wide open? Well, that gives additional attack surface that you're not going to think about from a feature perspective, but it still exists. And do I need to limit the capabilities of the services on a per user basis or a per role basis? User management in BMCs and like actual access credentials is kind of, it's very limited. I have very little control over what credentials I can authorize for certain behaviors. And am I actually using encryption for everything? Again, assume that this is going over the internet. Assume that somebody can subvert the network traffic. How can I know that, like, if you're not using encryption, you just need to be? And what about external connectors? Okay, well, I mean, the USB host one, hopefully that's self-explanatory, right? If they can plug an arbitrary USB device into your BMC and your BMC has drivers for it, then anything goes, right? There's never-ending list of attacks via USB. Now, why are you actually providing this? Often it's like a recovery path for your BMC. Well, in that case, how are you actually verifying the contents that you're updating from that USB stick? Because how do I know that this is actually an intended authorized update to this machine? VGA. Okay, why do I mention VGA? It's an output-only device, right? So, anecdote. When I was doing the initial Quanta Q71L support for OpenBMC, I started with the AST2400 support from Palmetto. And the amount of RAM installed in the system is different. And the allocation or the straps for the VGA frame buffer were different. So when I actually booted that BMC image the very first time, I wasn't getting video output that made any sense. It was just complete gibberish. And that's when I realized that, in fact, what I was looking at was a section of kernel memory dumped onto my VGA output as though it were a VGA frame buffer. Right? So think about these things of the host gets access to the VGA port. So like, where is this frame buffer located and what can happen if I steer that wrong? The VGA port becomes sort of an automatic data output device, even if the host isn't really doing anything. And what data are you going to show there? Like, if I do give it to the host, then it's the host's problem as to what information they show on the VGA device. But if I actually have a stage where the BMC can take control over the VGA and display something, I got to think about what I'm actually displaying there, because somebody could have just taken a crash cart and plugged in. Similar thing with the serial ports. I mean, just what am I actually allowing access over this, and how do I know that it's trustworthy? Just because it's a physical serial port does not mean it's trustworthy. Okay, so let's do a case study. If you haven't paid attention to the news today, this got revealed 6 a.m. Eastern time. This is some research I've been working on since June-ish. So USB Anywhere. First of all, responsible disclosure timeline. As I said, I've been working on this since June. I've been working with Supermicro to actually get this fixes out in place and make sure that people affected by this that I'm able to get in touch with have been notified. So this all started from a question of how does the virtual media service work? So if you've never used virtual media, the idea is that if I launch the IKVM application, then I have the ability to type on a keyboard and use the mouse and get video. It's kind of like using VNC, but it's actually connected at the hardware level, so I can play with BIOS, I can do all sorts of things. Well, but it has this feature for being able to mount a ISO disk image as though it were a CD-ROM drive on the remote machine. And I thought, that's kind of clever. How do they actually make that work? This seems like it could be ripe for poor implementation. Okay, so what do I know? Well, I know that in the case of the Supermicro machine that I happened to pick, I actually looked at a lot of different machines. It just happened to be the Supermicro one was the one that was most interesting. So on the Supermicro machines, the BMC serves me a Java applet via JNLP. So essentially it hands me a little metadata file with some setup arguments and tells me to go fetch a jar. It serves me the jar and I actually launch an application with a couple of arguments. Inside of that Java application, I can mount an ISO, and that ISO is located on the machine that's running the Java application. Now, when I click the plug in button in the UI, that ISO shows up as a USB device on the remote host. So if I'm running Linux on the remote side, I can actually look and inspect, and I see a mass storage device using the SCSI transparent command set that shows up as a multimedia device, aka CD-ROM drive, and it provides some information as being the A10 virtual CD-ROM. Okay. Now, I also know that from looking at the LS USB output and other things that the IKVM also implements its keyboard and mouse as virtual USB HID devices. Okay, so this tells me a couple of interesting things. If I go back and look at the connections that are available between the host and the BMC, I know that the the host USB host port connects to the virtual USB hub on the BMC. So let's go looking at a little bit into how that USB hub actually works. So a virtual USB hub in a BMC is a couple of devices, and a whole pile of separate endpoints. So in USB nomenclature, an endpoint is a unidirectional pipe. It's going to let you send data to the BMC or get data back. And a device is some sort of description of all of the metadata associated with a set of endpoints, and it identifies some function on the actual USB device. So on the machine I was looking at, the BMC there supported one hub device, and then underneath that it had 5 downstream devices. And each of those devices could then allocate any of these 15 endpoints to those devices as it wanted. So the actual configuration of the USB devices is entirely up to the BMC software. I can be any USB device I want. And that kind of makes sense, both in keeping the actual hardware design simple, but also providing a lot of flexibility to the firmware. Okay, but remember, back to our threat model, if I've thought through the traffic that can come over USB, and I know that the hardware allows me to do anything, now I got to think about what can happen in the software. Okay. Well, first of all, let's switch over and look at the LAN attack side, right? Because actually going in and figuring out what the firmware is doing with that USB peripheral is going to be hard work, and attackers are lazy. So if I go look over the network and I grab a Wireshark trace, I see, first of all, some HTTP traffic. I knew that because I had to go get the JNLP and the Java jars. I see VNC, which makes sense for the IKVM. That's pretty common. But I also see port 623 TCP. And this port only shows up once I actually open the virtual media UI window. Okay, that's a good indicator that something interesting is happening there. But nobody knows anything about what this protocol is. Okay, well, let's start poking around inside of this packet. Well, hang on. A10 virtual CD-ROM drive. I've seen that string before. Now, if I can see that in the raw packet dump, that means there's no encryption. So what's going on? Well, there's this other string that says USB-S. What is this? Well, if you Google for that, thank you, Google, for being a sponsor. You get that this is actually a signature for the response. So the command. So there's a command status wrapper inside of the bulk only transport of the USB mass storage class. And so this is actually 4 bytes that identify that this is the status response to a command issued over USB. So now I know not only is it unencrypted, but it's actually sending USB mass storage bulk only transport data directly over inside this on this port. So with a lot of work and staring at things and actually having to dip into the firmware and reverse engineer things, I was able to actually figure out the entire protocol. And there's a couple of things to note. This is actually the device setup. So there's a particular packet that carries over the credentials and the actual USB descriptors for allocating a device. And a couple of things to note, there's a bit that indicates whether or not the payload is actually encrypted. It's up to the client to decide whether or not to send it encrypted or not. Now, the Java application actually does choose to send it encrypted, but I don't. And then there's also a set of flags where that indicate, is the username a session ID? So essentially, in the case of a normal, in the Java application, part of the JNLP packet is actually a unique session ID token that then it gets used to send as the username and password. But if I set that bit to 0, it accepts a plain text username and password. Interesting. But it gets worse. So you may have noticed that there was actually a couple of panes here that show frame and decrypted payload. So we talked about encryption as being optional. Well, it's actually RC4, not exactly a stellar encryption algorithm by today's standards. They actually use the exact same key on all of their X9, X10, and X11 BMCs. They just never changed it. And they could have actually implemented it so that every packet was encrypted, but it doesn't. It only encrypts that setup packet that includes the credentials. Everything else is entirely transparent. The USB device is entirely implemented on the client side. That Java application actually has a JNI that is a native library that implements SCSI command protocol and ISO reading and handles all the USB packets. And ultimately, when you send that setup packet and authentication, you also send all of the descriptors for the device. The server does cache those so that it can respond to USB setup requests fast enough. But everything else, all the endpoint traffic, is sent directly over to the client, and the client's responsible for it. So the client's in complete control of what happens on the USB interface going to the host. Now, it also turns out that when they were implementing this on X10, X11, somewhere along the line, they decided that they needed to cache some internal state. And part of that is the credentials. It appears to be some sort of mechanism for if I temporarily lost connection, that it would come back within a certain time window. If I reestablished a connection, I don't really understand. But ultimately what it means is that when the client disconnects, they fail to actually clean up, or they have a cache that is associated by the socket number. So essentially the socket file descriptor number. It's not technically a file descriptor, but the socket number. And the credentials are part of that cached information. And when on a client disconnect, it doesn't actually clean up that state. So if you connect again and happen to get the same socket number, it completely ignores whatever credentials you send to it and just uses the cached ones. So as long as somebody has used the virtual media service once before, since the BMC was powered on, which happens when you attach the power, and won't reboot unless you did like a firmware update or crashed it or pulled the power to the machine, then also remember that BMCs tend to only have one user at a time. And given how the Linux kernel recycles socket numbers, when that user gets disconnected, if I connect, I'm pretty much going to get the same socket number. Most of the time, I can actually just reconnect and it completely ignores all the credentials. So in a good case for an attacker, bad case for everybody else, I have unauthenticated access to raw USB traffic to the host. Okay, well, what can I do with that? Well, FaceDancer is a Python framework for emulating USB devices. Now, this was originally designed for some special purpose hardware called the FaceDancer 21. And over time, it's gained sort of a plug-in architecture for the backends. So you can basically write Python applications that are the USB device, and then use hardware to actually make it show up as a USB endpoint or USB device to some target host system. So I just implemented a new backend, right? I don't use encryption. I use plain text, username and password. And this is a proof of concept quality, right? So it's not excellent, but it's good enough. So what can I do with this? If you can't see this clearly enough, it's available online as well. So here I am logging in to the interface. Yes, it's the default credentials, but imagine it wasn't. I'll go over here and I'm going to go ahead and fire up the IKVM. Okay, so on the left, we see the actual IKVM application starting. Okay, now I'm logged in as root on this machine. This is just for convenience sake, right? It could be anything. And on the right-hand side, I'm actually on my Windows laptop in PowerShell. And here I'm just pinging it to show you, this is actually like quite a ways away. It's like 35 millisecond latency. I was actually over a VPN from San Jose to Portland. So here I'm just going to go ahead and create an empty file, empty like 16 megabyte file. Great. Notice on the left, the USB devices, there's some A10 devices. Those are the keyboard and mouse and the virtual hub. But there's no, the SanDisk is actually an actual SanDisk plugged into this machine. So on the right here, I tell FaceDancer to connect to that machine's BMC and emulate a USB mass storage device with that disk image or with that empty file as the disk image. And you'll notice that it connected, and actually there's a new drive on the Linux machine. We do a little bit of detail look here. Yep, there's a new device. It's got a very odd username or UID PID. Of course, that's completely under my control, so I can make it whatever I want. If I take a look at the details of that, comes back. Okay, so I'm presenting a mass storage SCSI device. In this case, the endpoint addresses are 1 and 2, but I was actually making them prime numbers before just to see that I could have fun with it. Strings I don't get to control. That's a limitation of the protocol. But clearly, you know, I have access to this device, and I can set up the type of device I want. I also had a prototype of a keyboard, but it's trickier to make it work correctly. If I look at the dmessage output, you see that it actually goes and finds it. And notice that the identify information is actually called GoodFet. That's another hardware project that's another backend for FaceDancer. So here I can run the SCSI inquiry and get a response. That's entirely implemented on the Python side. So now I'm actually going ahead and partitioning the drive. Setting up a small DOS partition. It actually took me a while to figure out how to get it to not crash when it was sending so much data over. Turns out with that much latency and the large writes, there's some instability. But after I wrote that, go ahead and make a fat file system. And in this case, I'm just going to go ahead and copy etc password onto my file system, unmount it. And detached the USB device, it's gone. Yes, there's some log messages that indicate all this happened. And here we're going to go and just actually search the output for root because I copied over Etsy password. And so I kind of expect to find this. It takes a moment. But as expected, I get the contents, right? It's simply buried in there. It's a normal FAT file system. Okay, so the impact of this, once I found it, I knew that people hook BMCs on the internet, so that's bad. I did a scan of the internet. 47,000 affected BMCs were on the internet. They span 90 plus countries, 1,900 ASs, so 1,900 separate network operators. And this says nothing about how many are on enterprise networks, right? This is simply what's literally open on the internet. The list is, you can do whatever you want with USB attacks. The list of possible attacks is endless. So putting all together what we've talked about today, if you're an end user of a server, protect your existing BMCs. They're very privileged and very vulnerable, right? Treat them like you would if you plugged an unpatched Windows XP machine onto your network. You do not want it to be accessible by most things. Start working on updating your infrastructure. Redfish is coming up as a replacement for IPMI. If you can move that way, figure out how to move that way. Be prepared. Whatever's holding you back from actually hardening your BMCs and limiting access to it, like go through and start figuring out those policies and understand what do I need to actually start locking these things down. Put pressure on your vendors. Vendors look to the customers to figure out what they need to do. The vendors are not going to add security unless you actually ask for it. Or you file a vulnerability disclosure with them. Ask about the roadmap, right? See what they're actually doing in terms of security on the roadmap. If you're an OEM, first of all, please establish a security response team. It's really hard when you find a vulnerability and you have no idea who to contact at a company, and especially hard when you segment it by business unit. And so I have 5 different places to ask who actually deals with this product. There's actually an ISO standard for how to set these things up and how to handle vulnerabilities disclosures. So if your company does not have one, please do this. Think about how to make deploying BMCs safe, right? What are the defaults that would make it safe for me to plug a BMC on the internet? We know nobody should be doing this, but they do it anyway. So how can I make it okay? Things like generating per device default passwords and certificates, guiding them towards modern protocols, maybe just default to IPMI disabled and make them enable it. There's ways, right? And challenge your BMC firmware and SoC vendors to do better. I know that most OEMs don't write their own firmware stacks. Those that do, please pay attention to the next slide. But if you don't, just be in contact with your actual BMC firmware vendor and say, like, security is important to us. We need to solve these things. Get security audit results, right? They should be doing security audits of their code base. If you're a developer, expect your machine to be attacked. Expect every interface and every feature to be misused. Get used to asking yourself, what can go wrong? How can a user actually abuse this in some way? Insist on improving this security. Go ahead and design in secure boot. Even though you might not be being asked for it, like, start adding that into your design and start solving the problems, because it's going to take time. Make sure you move those modern protocols up on your priority list. Make sure they are available. Your customers may not be using them yet, but they can't use them if they don't exist. Start folding in security tests into your CI process. You want to find, just like your code breakage, you want to find security breakage as fast as you possibly can. Things like Metasploit are going to easily show you what's available to you in for IPMI type attacks and things like that. Go ahead and just start folding this into your testing. If you want more on USB Anywhere, there's a blog post, the POC demo video if you want to see it more. Also, there's a GitHub that actually includes some of the tools. It does not currently include the FaceDancer patches. Those are being upstreamed to FaceDancer. but there's packet captures and some other tools and other information about it. All right. Thank you.